Hello everyone, I am AJIKUMAR, Assistant Professor, Mechanical Department from Rohini College of Engineering and Technology. In this video, we are going to discuss about the subject Finite Element Analysis. The subject code is ME8692. In this video, we are going to discuss about one-dimensional bar element problems. We are going to discuss two problems in bar element. We already discussed clearly about the bar element stiffness matrix shape function and finite element equation in the Unit 2 Part 1 video. So this is the second video of Unit 2. So the first problem is a steel bar of length 800 mm is subjected to an axial load of 3 kN as shown in figure. Find the elongation of the bar. We want to find the elongation, that means displacement of the bar element, and it's given as neglecting self weight. So the total length given is 800 mm. So we want to divide this bar element. Before doing this problem, we want to divide the 800 mm into equally as a two element as 400 mm and 400 mm. Length of the first element is 400 mm and length of the second element is 400 mm. Like shown in this figure. So length given is 800 mm. When we are dividing into two elements, L1 is 400 mm and L2 is also 400 mm. So the load acting in the bar element P is equal to 3 kN. So we want to put 3 into 10 to the power 3 Newton. Kilo, we want to change this to 10 to the power 3 Newton. Young's modulus given is 2 into 10 to the power 5 Newton per millimeter square, and the area given is 300 millimeter square. So we know the finite element equation of bar element, that is F1 F2, that is equal to A E by L, 1 minus 1 minus 1 1, matrix of U1 U2. So we want to consider the element 1. When we are considering the element 1, the nodes should be considered as 1 and 2. So the equation is written as A1 E divided by L1, 1 minus 1 minus 1 1, U1 U2 is equal to F1 F2. Why we are putting as A1 means we are just showing that is the element 1's area, that is K1. L1 is also the length of the first element, so we are mentioning it as L1, but we are not mentioning as E1 E2 because it's the same element. It is a steel bar. If it is given, if the first element is steel and the second element is aluminium, means we can mention it as E1 and E2. Otherwise we can mention it as ES or EA like that, but it is the same element steel bar, so we want to mention the Young's modulus as capital E only for both the element 1 and 2. So given area is 300 into Young's modulus is 2 into 10 power 5 and divided by length of the first element is 400. So we want to substitute the values and we will get the nodal position, that means stiffness matrix for the first element is K is equal to matrix 11, 12, 21, 22. So A11 is 11 and A12 is 12, A21 is 21 and A22 is 22. So we want to mention the nodes, that is 1 and 2 in the upper side and also the right side of the matrix, because when we are assembling the matrix, if we are mentioning like this, it will be very easy to assemble the matrix at last. So then considering the element 2, that is when you are considering the element 2 of the bar element, the node should be 2 and 3. So same, we want to follow the same formula for determining the stiffness matrix, that is A2E divided by L2, 1 minus 1 minus 1 1, U2 U3. So in element 1 it is mentioned as U1 U2. In element 2 we want to mention as U2 and U3 because we are considering the node as 2 and 3. That is same F2 F3. So we want to substitute the values. The area of the second element is also 300 and the Young's modulus is 2 into 10 power 5 and the length of the second element is 400, and also in this also stiffness matrix we will get as 22, 23, 32, 33. We want to put the points at nodal nodes and the upper and the right of the matrix, that is 2, 3, 2, 3. So the equation number 1 is the stiffness matrix of element 1 and the equation number 2 is stiffness matrix for the element 2. Then we want to assemble the stiffness matrix. So when we are assembling the stiffness matrix, finally we get the answer as matrix of 11, 12, 13, 21, 22, 23, 31, 32, 33. So then 150 to 10 power 3, then we are substituting the values and in the finite element equation formula. Then we want to next step, we want to find the we want to apply the boundary condition and we want to find the elongation of the bar. So next we want to apply the boundary condition. So displacement at node 1 is 0 because it is a fixed node. So u1 is 0. And 3 into 10 power 3 Newton load is acting at node 3. In the third node, the force is acting. So F3 is 3 into 10 to the power 3 Newton. Self weight is neglected. It is given in the problem. So F1 and F2 is equal to 0. Then we want to apply these values in the assembled equation. So when we are substituting the values in the assembled equation, u1 we want to substitute as 0. We want to find u2 and u3 only. When solving this equation, at last we get the answer as displacement at the element displacement at node 2 u2 is 0.02 mm and displacement at node 3 u3 is equal to 0.04 mm. So at last we want to find the elongation. That the formula is del L is equal to PL divided by AE. That is P is 3 into 10 to the power 3 into length is 800 and the area is 300. Young's modulus is 2 into 10 to the power 5. So this for verification we are finding the answer. We will get the answer U3 0.04 mm. Same we will get the elongation is also 0.04 mm. So the second problem we are going to discuss the second problem. The second problem is consider a bar shown in figure. An axial load of 200 kilonewton is applied at point P. Take area of the first element is 2400 millimeter square and the Young's modulus for the first element is 70 into 10 to the power 9 Newton per meter square and the area of the second element is 600 millimeter square and the Young's modulus of the second element is 200 into 10 power 9 Newton per meter square. We want to calculate the following. That was, first we want to find the nodal displacement at point P. And the second one is stress in each material. We want to find the stress in each material. And the third one is reaction force. So what we want to find is nodal displacement at point P. Point P is acting in the second node. So we want to find U2. Then stress on stress in each material and also reaction force. So here the first element length is L1 is 300 mm and L2 is 400 mm. So in the second node 200 kilonewton load is acting, that is 200 into 10 power 3 Newton. Node 1 and node 3 is fixed. When we are applying the boundary conditions, we want to put U1 and U3 as 0. Same like the discussed problem 1. Same method we want to follow in this problem also. First we want to consider the element 1. Element 1 means we want to consider the nodes 1 and 2. So same formula A1E divided by L1, 1 minus 1 minus 1, 1, U1, U2 is equal to F1, F2. So that is we want to apply the area 2400 into 70 to 10 power 3 divided by 300. And we want when we are substituting these values and we will get the final answer for element 1 is 1 into 10 power 5 matrix of 5.6 minus 5.6 minus 5.6 5.6 into U1 U2 is equal to F1 F2. Same for element 2, we consider the nodes 2 and 3. A2 E divided by L2, 1 minus 1 minus 1 1 U2 U3 F2 F3. Same we will get the answer as 1 into 10 power 5 3 minus 3 minus 3 3 U2 U3 is equal to F2 F3. At last we want to assemble the equation number 1 and 2, that is the stiffness matrix of the element 1 and the stiffness matrix of the element 2. When you are assembling the stiffness matrix, we will get the final answer as 1 into 10 power 5 5.6 minus 5.60 minus 5.6, that is 5.6 plus 3. That means that this is the meeting point of two nodes, that is 5.6 plus 3 we will get as 8.6 minus 3 0 minus 3 3 and U1 U2 U3 is equal to F1 F2 F3. Then we want to apply the boundary condition. Already we have discussed in the problem 1. Which node is fixed? We want to put the displacement value as 0. In this problem, the node 1 and the node 3 is fixed. So U1 and U3 is 0. Load is acting on the node 2. load is 210 power 3 Newton. So F1 and F3 is equal to 0. We want to consider the F2 is 200 into 10 power 3 Newton, and we want to substitute all the values in the assembled equation, and at last we will get the answer of U2. That means displacement at node 2 as 0.2325 mm. Then we want to put the stress equation. We want to find the stress. Stress equation is sigma is equal to E into du by dx. So du, what is du is, in this element 1 we want to consider as u2 minus u1, and element 2 we consider as u3 minus u2. So in the stress in the element 1, sigma 1 is equal to E1 into U2 minus U1 divided by L1, that is equal to 70 to 10 power 3 into 0.2325 minus 0 divided by 300. So we'll get the answer for stress. Sigma 1 is equal to 54.25 Newton per millimeter square. Same equation, same formula for finding the stress in element 2, that is sigma 2, that is equal to E2 into U3 minus U2 divided by L2, that is 210 power 3 into 0 minus 0.2325 divided by 400. We will get the answer for sigma 2 is equal to minus 116.25 Newton per millimeter square. Then we want to find the reaction force. The formula for reaction force is matrix R is equal to stiffness matrix K into displacement matrix U minus force matrix F. That here three elements are considered, 3 nodes are considered, 2 elements and 3 nodes are considered. So R1, R2, R3. We already find the element stiffness matrix equation. We want to substitute that, and we want to solve the matrix, and we want to find the final answer R1, R2, R3 as R1 is equal to minus 1.302 into 10 power 5. R2 is 2 into 10 power 5, and R3 is minus 0.6975 into 10 power 5. When at last we want to give a verification as R1 plus R2, we want to add the both reaction values R1 plus R2 plus R3, we will get the load as our answer, that is minus 210 power 3 Newtons. Applied force as the answer. So if we are getting this 210 power 3 Newton, we can assume that we done this problem. It's in a perfect manner. So hope you all understand about the stress and also stiffness matrix and shape function of the bar element problems. So we'll further discuss the beam element problems in the next video of unit 2. Thank you. Thanks for watching. If you have any queries, you can contact me in my WhatsApp number 8754330058. My mail ID is ajikumar.aero@gmail.com, that is AJIKUMAR.AERO@gmail.com. Once again, thank you.